In section 7.3, we're going to talk about similar right triangles. And the first thing we're going to talk about is theorem 7.4. And there's a lot of words when you copy down the theorem, and I'm going to show you what the gist of the words mean. The theorem states, if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So I'm going to draw it for you. An altitude connects the opposite side to a vertex, and it is perpendicular to the opposite side. I'm going to call this point D. So the way I'd like you to remember theorem 7.4, feel free to put this in your notes for theorem 7.4, is write an altitude to a right triangle forms three similar triangles. Okay, so what I'm going to do is the three triangles I get, I'm going to draw in the same orientation, and I'm going to draw them all like the ACB triangle is. This next one looks like this, because here's the hypotenuse, so I roll it down. And this one is going to be a BCD. So what it tells me is all three of these triangles are similar. Therefore, I know that I'm going to go in this order, A, B, C. Triangle A, B, C is similar to triangle in the same order, CAD, which is similar to triangle BCD. And again, from chapter 6, if you have similar triangles, the easiest way to do similar triangle problems is to draw the triangles in the same orientation and then set up proportions using those orientations. So make sure that you have this and these three drawings in your postulates and theorems book with this relationship. I'm going to pause the video while I erase the board, and then I'm going to do some example problems on how we use theorem 7.4. So the examples for theorem 7.4, they give you two right triangles with altitudes drawn in them, and they want you to find the lengths of the altitudes. The first part of the problem says to identify these similar triangles and then find the value of x. So first thing, to identify the similar triangles, we need to have the triangles in the same orientation to write the similarity statement. I'm going to just draw three triangles in the same orientation. I'm going to call the left side the short side, then the long side, and then the hypotenuse. So EGF. Okay, so that's the big triangle. Now let's look at this triangle. The hypotenuse is EG. The short side is, looks like it's going to be, let me try to draw this more perpendicular. If you actually look at the guided practice in your book, the short side is definitely EH, and the hypotenuse, so E, H, and then G. The short side of the lower right-hand triangle is definitely GH with the hypotenuse GF. So G, F, H. From that point, I can write my similarity statements. Triangle EFG is similar to triangle EGH, which is similar to triangle GFH. What I'm going to do now is I'm going to label my three triangles with the side lengths that I know. I know that EG is 3. I know that FG is 4. I know that EF is 5. And HG is X. The other thing I know is I know that EH plus FH has to equal 5. So I'm going to introduce 2 more variables so I can do this problem. I know that I'm going to call this one Y. So I'm going to have to do 1 more variable. This distance, if that's Y, so EH is Y, I know that FH is Y is 5 minus Y. Okay, the other relationship. So I know that those 2 relationships hold true. And I can now have 2 equations with 2 unknowns in them. I can solve this triangle, and I can solve this triangle using the Pythagorean Theorem. On the left one, actually I can do this one easier. If I want x, I have a proportionality statement. I have x over 4 is 3 over 5. X over 4, bottom over bottom, equals hypotenuse over hypotenuse. Multiply both sides by 4, and I get x equals 12 fifths. The work I'm setting up is what we need to set up to do one of the next theorems. So don't worry about this part right here. So once I fill out what I know, now let's check our work. I know that x over 3, short over short, is equal to long over long, 4 over 5. Multiply both sides by 3, and I get x equals 12 fifths. So either way you want to do it, once you draw your triangles in the correct orientation, you can use your proportionality statements. Next one's guided practice 2. Again, I want to draw all 3 of my triangles in the same orientation as my original triangle. Label my original triangle JML. I'm going to take this triangle, lay it on its side, and flip it around, so it's going to be MKL. This triangle, that's going to be the top, so M's on top, J, and then K. Label the sides I know. I know JM is 12. I know ML is 5. JM is 12. And I know JL is 13. I'm missing one here. Okay, MK is X and X. So I have 2 different options to write my proportionality statement to solve for X. I'm going to use this one first, then I'll check it with this one. I know that bottom over bottom, X over 12, is equal to hypotenuse over hypotenuse, 5 over 13. Multiply both sides by 12, and I get x equals 60 over 13. Or I can write right over right, x over 5, is equal to 12 over 13. Multiply both sides by 5, and I get x equals 60 over 13. So where you're trying to find the value of the altitude, if you're given all 3 sides of a right triangle, draw all 3 similar triangles, label the applicable sides, and then just set up a simple proportionality statement. Okay, and then it's basically going to be 1 step to solve for your remaining variable in most cases. I'm now going to erase the board, and then I'm going to go over the last 2 theorems of section 7.3. For Theorem 7.5 and Theorem 7.6, when you draw the pictures in your Postulates and Theorems book, I want you to label one of the A, B, C right triangles with CD as the altitude as follows. Label the base as the hypotenuse. I label the altitude as alt. Then I called the one on the right L1 for leg 1, the one on the left L2 for leg 2. BD I called P1 for piece 1, and I called AD P2 for piece 2. And I did that in both drawings on here because it's going to be easier to set up the proportionality statements in words. And let me just go through and read the theorem for geometric mean altitude. Then I'll discuss again what a geometric mean is. I've covered it earlier this year. And then we are going to write it out the way I'd like you to write it in your theorem book. It says, in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments that I'm calling piece 1 and piece 2. The length of the altitude is the geometric mean of the length of the two segments. If I have the following proportion, A over X equals X over B, we learned in Algebra 1 and earlier this year that is called the mean of the proportion. So what I'm going to do is I'm going to cross multiply, and that gives me AB equals X squared, and I'm going to solve for X. And this is what it means to be a geometric mean. A geometric mean, which is X, is the square root of a product. So a geometric mean is equal to the square root of a product. An arithmetic mean is equal to a sum divided by 2. So the geometric mean of two numbers is the two numbers multiplied together, then take the square root. The arithmetic mean, you add the two numbers and then divide by 2. So those are the two different types of means. This time we're dealing with geometric means. So it told me that the altitude was the geometric mean of these two pieces. So the way I want you to write down the theorem is that the altitude is equal to the square root of piece 1 times the length of piece 2. It says the hypotenuse divides, it says the length of the altitude is the geometric mean of the lengths of the two segments down here. This is the formula that you're going to want to use. That's the way I would remember it. The altitude is equal to the square root of this piece times this piece. So the geometric mean leg theorem states the length of each leg of a right triangle is the geometric mean of the lengths of the hypotenuse and the segment that the hypotenuse is adjacent to. So these are the two that I'm going to write geometric mean statements for. The length of the leg, they said, is the geometric mean of the length of the hypotenuse and then the piece it touches. The leg of a right triangle is equal to the geometric mean of the length of the hypotenuse and the piece that it touches. So that's the way I would like you to write the formulas for Theorem 7.6. Again, make sure you have these triangles drawn in your postulates and theorems for Theorem 7.5 and Theorem 7. That's Theorem 7.6 and Theorem 7.7. So make sure you have those copied, and I am going to do some example problems, and that will be it for the lectures for this week, because Thursday in class, I said you're going to take a quiz in the morning, the first thing of class. Then you're going to work on the classwork for the first part of this section. And then on Friday, there is no new video Thursday night. Friday in class, you are going to do the classwork for the second part of this section, and you'll have a video Friday night to watch for homework over the weekend. So the biggest thing to look at when I'm dealing with the problems for the second part of 7.3 is, am I using the geometric mean altitude theorem, or if I'm using the leg theorem? If you're trying to find a leg or given a leg, you use the leg theorem. If you're trying to find the altitude or given the altitude, you're going to use the altitude theorem. So the first one is problem number 13 from section 7.3. I want to find the value of x. So I'm going to label my sides. I'm going to call this L1, P1, P2, and I need to know what my hypotenuse is. My hypotenuse is those two added together, which is 9. So L1 and P1 is this relationship. L1, so that's x, is equal to the square root of 5 times 9. Okay, we know the square root of 9 is 3. The square root of 5 is the square root of 5, so my answer would be 3 times the square root of 5. For 14, I'm given an altitude and the two pieces. So I get the altitude and the two pieces. That's the way I'm going to write my equation. I know that the altitude is equal to the square root of the sum of the the product of the two pieces. I need to get y by itself, so I'm going to square both sides. And 18 squared is 324. And that's equal to 12y. Divide both sides by 12. And I get 27 is equal to y. So those are straightforward problems. The next thing I need to do is, I've given you two pieces out of the whole triangle, and I want you to find the remaining pieces. Now we've got to come up with a plan. We want to use the easiest methods possible to come up with the missing pieces. To me, the easiest method is the Pythagorean Theorem. So this is a right angle, so I know that z is the square root of the sum of the squares. So square root of 12 squared plus 16 squared, which is the square root of 144 plus 256. And just want to make sure. 144 plus 256. That is in fact the square root of 400. So z is 20. Okay, I know I can find the x using the altitude theorem, because I know that 12, which is the altitude, is equal to the square root of these two pieces. Square both sides. Divide both sides by 16. And I get x is 9. Okay, now I can find out y two different ways. I know that this is 25. I know this is 20. So that looks like a 5. That's a 4. That would be a 3. So that would be 15, just by doing a 3, 4, 5 Pythagorean triple. Or I can use the Pythagorean theorem here. 9, 12, 15 would be another Pythagorean triple. Or I can use this one. I'm going to use that. I know that L2 is equal to the square root of P2 times the hypotenuse. So y is the square root of 9 times the hypotenuse, which is equal to the square root of 225, which is in fact 15. So again, we're using all of chapter 7 to start solving some of these other triangles that are right triangles created by dropping an altitude from a right triangle to the hypotenuse. So make sure you have all your notes done. You have the theorems written up the way I asked you to write them up. Do the practice problems that I assign each day. Make sure you have those ready for class, because those are what we'll do at the beginning of class.